In a single eruption, this volcano can release millions of cubic meters of material rock, ash, sand. Enough to bury landscapes and reshape entire river systems, but when the eruption ends, the real transformation begins, because what looks like destruction will become the foundation of modern infrastructure. When molten lava cools, it solidifies into dense volcanic rock. Ash settles into fine sediment. Fragments harden into gravel and stone. Basalt and andesite form along the slopes. Over time, gravity and weather begin their work. Large rocks fracture into smaller pieces, stone becomes gravel. Gravel becomes sand. The mountain reshapes itself slowly and constantly. Rainfall activates the next stage. Loose volcanic deposits are mobilized by surface runoff. Water mixes with ash and fragmented rock, forming sediment flows. Cold lava currents, known as laha, can transport enormous volumes downstream. Multiple rivers descending from the mountain act as natural conveyor systems. They distribute volcanic sediment into wide riverbeds where it accumulates in layered deposits. What was once airborne ash now becomes structured sediment. To manage this constant movement, engineered check dams are constructed along volcanic rivers. These structures slow debris flow, trap large rocks, and reduce downstream flooding risk. Behind each dam, controlled sediment zones develop. Stable accumulation areas form. Predictable, measurable, and nature produces the volume. Engineering organizes it. Within designated river sections, Volcanic sediment is extracted systematically. Excavators operate across broad riverbeds, lifting layers of sand, gravel, and larger stones. The material is sorted by size and density. Large boulders, medium-sized rock.gravel.fine volcanic sand. Screening systems separate usable aggregate from oversized debris. The process is mechanical and controlled, yet always influenced by terrain stability, river shifts, and weather conditions. This is not random digging, it is structured industrial recovery. Volcanic riverbeds contain multiple grades of construction aggregate. Large boulders are used for riverbank protection and structural reinforcement. Crushed stone, often called split aggregate, forms the backbone of road foundations. Gravel improves drainage and stabilizes concrete mixtures. Fine volcanic sand becomes a primary component of mortar and reinforced concrete. Each size fraction serves a different engineering function. Modern infrastructure depends on aggregate. Highways require compacted base layers capable of bearing continuous heavy loads. Bridges rely on reinforced concrete with precisely graded sand and stone. Urban expansion depends on stable foundations. Without aggregate, construction stops. In many regions, volcanic deposits provide one of the most durable and consistent sources available. What once erupted violently from the earth now supports engineered stability. Once sorted and processed, the material is loaded into dump trucks that each truck carries up to 20 tons. From riverbed to crushing plant, from processing facility to construction site. But once fully loaded, gravity becomes part of the equation. And this is where the industrial challenge truly begins. Behind every road, bridge, and building is a source few people consider. Volcanic eruptions may appear destructive, but over time they generate essential construction material. Nature produces the raw resource, engineering manages it. Industry distributes it. Every loads river tons of material. But once fully loaded, the real challenge begins. Steep volcanic roads, overheated brakes, unstable ground. Because moving 20 tons downhill is not just transportation, it's a calculated risk. And that is where the next story begins.